Our next session delves into the foundations of XR interactions of head-mounted displays, an area central to creating seamless and engaging user experiences. It's my privilege to invite Dr. Pawan Prasad. He's the head of XR interactions at the team at Samsung R&D Institute India, Bangalore, where he leads the development of advanced interaction technologies for head-mounted displays, including hand tracking and eye tracking. May I now request Dr. Pawan Prasad to take the session.
Good afternoon, everyone. So, is it audible? Is it audible? Audible? Okay, all right. Good afternoon, everyone. I hope everyone had a nice lunch. I know it is like post-lunch, it is pretty challenging to focus. So I will try to keep it as less heavy as possible. So I'm really sorry about, if it becomes really difficult through the presentation. So, but yeah, I think we have some things interesting today. So we are basically looking at the foundations of XR interactions for head-mounted displays here in this particular topic. So we are looking at three topics. One is hand tracking, eye tracking, and face tracking. So we are working on all these topics. So we have worked on these topics for our Galaxy XR device, so which we recently launched. So I think we have a device prototype as well. So if you guys want to see it, please check it out as well. So let's look at what really motivated us in terms of building, a very, very intuitive interaction experience for our head-mounted displays, right? So as humans, right, so we basically interact with our world through, 3 or 4 means of communications, right? One is through our eyes, hands, face, and most importantly, our voice as well. So the device that we wanted to bring in to the world was how we could basically bring in all these multimodal interactions together where you can seamlessly interact with the device, right? So that is where the core of interactions was, kind of like the foundation was built, right? So that was the primary motivation in terms of why we wanted to have a very, very intuitive way of interacting with the device, right? So moving forward, right, so like I said, there are like all of these modalities, so where you would use your hands for some certain specific tasks. So the same way, like how intuitively, so we wanted to keep the learning curve as less as possible. So we didn't want to have the user to be able to do something extraordinarily different to be able to use a head-mounted display, for example, right? I mean, as we are moving towards, more seamless glasses and so on, like I think we have seen a lot of presentations from the morning regarding how the AR, VR landscape is kind of going forward, especially from, where it started from head-mounted displays going towards glasses and so on, right? So most importantly, right, so why all of these interactions come together, how they come together is what we're going to learn today, right? So firstly, let's introduce our device. So we call it as the Samsung Galaxy XR. It's a purely multimodal interactive device. It's a AR and VR capable mixed reality headset. It has several sensors, both world-facing as well as user-facing. As you can see, there are IMUs, there are tracking cameras, there are world-facing cameras, which are like these RGB cameras. There are also user-facing cameras, which make you intuitively interact with the device seamlessly. So all of these sensors are perfectly well time synchronized so that the data that it captures at any instant of time is given into the AI engine that is either running on the device or running on the cloud to be perfectly in sync with the device as well, right? So we do have this device. I mean, we don't have a booth as such, but yeah, but we do have the device at us. So if you guys want to experience it, you just come to us, like you can just catch us, and then we will be happy to show it to you guys. Right, so let's look at hand tracking. So one of the primary mode of interaction of this particular device was hand tracking. So why hand tracking was important is because it's very natural to be able to interact. So as you know, while we are moving away from a smartphone device towards a head-mounted display, right? So everybody is so used to using a smartphone with certain type of intuitive interaction, right? For example, the touch screen. For example, the voice-based navigation, voice-based gestures and so on, right? So now how do we basically move towards a more immersive content? So you cannot really see your hands when you're wearing a headset, for example. You don't want to like really like worry about where your fingers are and so on. It needs to be like, super intuitive. So we need to be able to track at really, really micrometer precision the landmarks of your hands, for example, right? And also the most important thing is it needs to be done in super real time on a device which is really low power, and at the same time we need to be able to have it such that there are many different things that we need to solve. It's not just about landmark tracking. So we'll basically learn about what are the core components that we need to build to be able to give you a very, very immersive interaction experience, right? So these are the three core components that we built for Galaxy XR. The first is the landmark estimation. So basically you should be able to identify, like I said, at millimeter precision. Number two is the gesture recognition. So we need to be able to interact with that with the device with very, very minimalistic, very simple gestures, and that needs to be that needs to work really, really well, right? When you say something in terms of a gesture, it should really, really work in real time. And number three is, of course, we need to be able to also visualize what we are doing. So when you're basically in an immersive experience, you need to be able to also render in real time the hand mesh that what we basically are seeing. So which is basically a replica of your real hands. Right, so these are the three main components. So some of the engineering challenges that we faced in terms of building such technology was these. So for example, occlusion is a very, very basic challenge, right? So when you're basically wearing a head-mounted display, a device which are looking at the hands, for example, the self-occlusion is very, very common, right? So your own hands will kind of occlude some parts of your hand, right? So if I look at it like this, right, obviously these landmarks are occluded. So this is very, very challenging, like in terms of like what do you do exactly when some of these are occluded, right? How do you basically give an experience to the user? So even these very, very small, tiny bits like this, needs to be really, really put effort in terms of how we focus. And secondly, in terms of the limitations are the egocentric FOV. So the most important challenge that we faced when we built this device was how we're going to place these sensors. Right? So the sensor placement was very, very challenging because we had to understand what are the baselines. Like for example, every small change in the baseline of these cameras, what is baseline is the distance between the two cameras, right? So we have basically mounted 14 cameras or 14 sensors on the device. If we want to basically have a very, very optimized viewpoint of the world, even a small change in the sensor position, sensor orientation, how it is oriented towards the user, right? So all of this matters a lot purely because, you may think that it's like, okay, it's just like rotating it, but you can see the device form factor itself, right? The mold of the device. It cannot really support all kinds of orientations of the cameras, for example. That is where it becomes really, really challenging, and it's a very, very constant interaction with the hardware team and the software team where we'll go back and forth. So they give us some ideas in terms of, okay, this is how we could possibly position the cameras, and next they basically come back and say like, okay, no, we could not do it because if you want to have a very, very comfortable feel of the device, they want it a certain way. So if you look at in the typical HMDs, right, so it's not just about solving technical challenges or engineering challenges. It needs to also support comfort. For example, when you're wearing the device for long hours, right, comfort is one of the important things. So all of these needs to come together in terms of but we really actually need to solve the actual problem of trying to collect data from the user and trying to solve the interaction problem as well. So as you know, it's kind of very easy to break. So because the interaction topic is something that it is directly affecting the user. Even a small inaccuracy, the user will get frustrated and they take the device and throw it out. Right, so you can imagine the kind of challenges that people really face in terms of making this kind of a product at a product level, right? To take it to the user. So these are some of the works that is happening, in our lab. So basically, we are building a lot of capture rigs where we basically capture a lot of ground truth data. So we do train a lot of these models to be able to track these landmark points and so on. So these are some of the works which also published as well. So here we do the landmark estimation, for the hands, and we also built our own in-house, multi-camera capture system, which is synchronized with almost 200 cell phones to be able to build a perfect ground truth. right? So we also worked, we also worked on building. So as you can see, right? So this is we talked about 3D hand model and so on. Right, so this is what we see today, like, I mean, like boring meshes and so on. So we want to be able to demonstrate like your hands in the live VR views. So we're also working on like topics such as text to 3D, where we can basically move forward towards generating different 3D models. So this is one of the works that is happening in our lab as well, where we basically build text to 3D models, where the user can really define what kind of 3D models they want, and it can generate almost kind of in real time, so that it goes to the cloud, generates this and comes back. So these are some of the things, new things that are kind of coming up as well. So where we will have a very, very intuitive way of how device and human interaction is made possible. So going forward, I think we'll look at more challenges that we have solved in our lab. So I invite Dr. Anup to kind of come and talk about eyes now. So thank you, Anup. Thank you. So we'll take the questions at the end of this presentation. Sure.
Is it audible? Yeah. Okay, thank you. Good afternoon all. So we'll go into the next mode of interactions, mainly eye tracking in a XR device. So yeah, so what is eye tracking? So essentially, if you look at this image, like the person is looking at a screen here, and essentially he looks at some point here, which we call as the point of gaze. And for a screen, it would essentially be XY coordinates. So this is referred to the movement of these eye, and where he sees on the screen, the coordinates essentially are what we track or call it as the eye movements. And mainly as a setup, it consists of illuminator, mainly the LEDs around, so that like you illuminate the eye pretty good. And then you typically have a IR sensor to capture the user eye image. And it's IR because like it gives you a very good contrast of the eye, and also there are glints which needs to be visible to get a good geometric model. And why eye tracking? It's very fast, convenient, and it's a low technological learning overall. So you don't really have to worry too much on how to use it. And yeah, I also like it gives you a window into what users are looking at, and kind of like gives essentially like some thought process that is happening by looking at their eye movements. Yeah, oops. Yeah, typically like previously, if you see an eye tracking setup, it would have an eye tracker here and a chin rest, so that like there is not much of head pose movement, which would cause a lot of inaccuracy if there is a lot of movement in the head. Later on, we could just come down to removing the chin rest here by improving the overall head pose estimation and correcting for the eye tracking accuracy. And this is where we are today. So essentially, you have the XR devices which you mount on your eye, and there are like eye tracking cameras mounted on them, and there is a scene camera looking outside. Okay. Yeah, I think one of the important things in eye tracking is to understand how the eye is. Essentially, it consists of the outer cornea, which is a bulge, and there is a aqueous humor here. So both have their own refractive indices. Then you have the iris region, which is the color region, which indicates a lot about the biometrics and the identity of the user. And then you have the pupil, most important in an eye tracking application, which controls the amount of light that passes through the eye. And then you have the lens, which focuses this light onto the retina region. So one of the important parts in the retina is actually called the fovea, where the visual acuity is the highest overall. So in general, for an eye tracking application, we'll be mainly looking at the iris regions. Then you have the pupil region, and there are glints. We'll come to what glints are. And typically, an eye can be modeled as a two-sphere model, one for the eyeball, the other is your cornea curvature, and the line or the ray that passes through your cornea curvature center, and the pupilla is called as the optic axis, whereas there is another thing called the fovea axis or the visual axis, which passes from the fovea to the center of the cornea curvature, also called the nodal point. Now, what is the problem here? So essentially, every user have like different eyeball radius. It's not the same. And also your cornea refractive indices varies from user to user. And essentially your fovea regions also not constant. For instance, like every user might have different visual axis altogether. But geometrically, we can only calculate what the optic axes are, and how do we personalize this. So that is the process of eye calibration, which is the most important part in any eye tracking hardware as such. So in typical calibration, we show different points on the screen like this, and the number of points depends on the hardware, like what is the FOV region. More the FOV, you need more calibration points so that like, you get better eye tracking accuracy. So through the calibration process, what we essentially do is like we get the optic axis from the two eyes here separate, and the point of convergence essentially is called as a binocular gaze, which is adjusted to the device origin. And then given those calibration points, which are also called as a ground truth point, you will learn a mapping from your optic axis to the screen axis or the visual axis. The important metrics in eye tracking is essentially accuracy and the precision. So here, like, though the precision is pretty good, is way off from the center, which is the accuracy. And this is the ideal case where you have overall good accuracy and precision. And this is like poor in both the cases. And finally here, though the accuracy is good, there is poor precision. Essentially, like, there's a lot of eye gaze jitter that is happening, which requires filtering overall. Eye tracking approaches can take eye tracking typically has two approaches. One is your geometric models, which mainly consists of estimating your pupil center, its ellipses, and also using the glints. And there are like deep neural models, which are also called the appearance models, which can use all this information along with the actual eye image. Geometric pipeline usually consists of your input image followed by a feature extractor where you're able to extract the different regions of the eye, mainly the iris, here the pupils, sclera, and the glints, and then you fit a 3D model to it. And in your inference part, based on the 3D model that you have, you estimate a 3D pupil position, and then the user calibration happens, and then you eventually get the gaze. Yeah. Some challenges in the pupil-based models. So as I said earlier, like different users have like different kind of like refractive indices overall, which we call the corneal refractive index. And as such, if you see the two images here, they have the same gaze, but because of the different refractive indices of the cornea, they actually look very different geometrically. As such, like if you're not accounting for it, for the corneal refractions, the gaze accuracy can go down. Additionally, like there is another problem called as a device slippage, like you're wearing the device and you're moving. The device can move up and down, which can affect your eyeball center estimation, which would eventually cause a drop in overall accuracy in your gaze. This is one of the typical geometric models. It is called PCCR, pupil center and the corneal refraction. Essentially here, like it has a different LED light source here. So this falls on your corneal region, which causes a reflection, and it's captured by the image. And this is actually called as the glints. So knowing the geometry of your light source and the glint and all the corresponding pairs, and using the law of reflection from physics, you can actually estimate the overall center of this corneal curvature, also called the nodal point. So this is the main part, like overall estimating this point. So once you get this point, you can easily estimate the optical axis using the pupil center. The other type of methods which are becoming popular because of its efficiency is appearance models, typically done using deep neural nets. And this essentially consists of like extracting your right eye and the left eye and passing through some convolution layers. Additionally, we can also put in additional landmarks as to pupil centers or any sclera regions as such. And finally, train it to learn a good gaze point. And this can also be modeled as to include the user calibration overall, where you have a feature embedding for each appearance faces that you have. And this can be learned on device using, say, some federated learning methods. And also, you can also put additional constraints based on gaze directions. Yeah, visualizing eye tracking typically has two ways of looking at it. One is your fixations and the saccades. Fixations are like the circles you see here. So it typically refers to the dwell time, like amount of time you're actually looking at, and typically refers to the visual attention. Larger the circle radius or the amplitude, it tells like user has additional attention on it. Whereas the saccades are like the rapid eye movements. Your eye movements actually are not stable in general. They move a lot, and this temporal information is referred to as the saccades. And in general, this can be visualized also as heat maps, And denser, the darker the regions, essentially you have more visual attention here. And typically for humans, especially like you see an image with faces, majority of your attention drives towards the faces. Coming to the use cases, yeah, one is like basic interactions in a AR, VR applications. You can use eye tracking. Then there is another important application called as a foveated rendering. Essentially, if you look at this image, you want to display this image on an XR device, and say with a resolution of 4K and 4K rendering, each pixel is a lot of power consumption. So here, what they actually do is they concentrate on this foveal region, essentially where the user is actually looking at, so that like they can concentrate their entire compute resources around this region, whereas around the peripheral regions where the user is not looking at, you can have reduced computation or rendering overall. Then you have the visual understanding, like basically understanding the visual attention of a user. And also in, say, marketing and advertisement, say you are going into a supermarket, so you can know like where the actual users are actually looking at into different racks, and you can decide on what you want to place in these racks. And finally, you have the healthcare, where you have the driving safety alerts that can be given based on the eye movements of the user. And also like diagnostics, some certain medical conditions like autism, where like the users are not able to have proper attention and kind of like they have a rapid, fast eye movements overall. Coming to the challenges here, so the first problem is what is referred to as the eye relief, and this is very device dependent. Eye relief is essentially the distance from your eye to the lens, and typically the eye tracking cameras are behind the lens here, and if the eye is very far off, you actually don't see much of the features that are required for eye tracking. So this has to be very optimal so that eye tracking performs pretty good. Then you have the eye disorders here. So, yeah, it's not visible. So generally, like your pupil is elliptical in nature, but if you have undergone some surgery, they undergo a lot of deformation. So your geometric models are prone to failure here. And then you have obstruction of features from external medium like glasses. So here, like a user is wearing a glass here, and it introduces a lot of additional flares, which can interfere with your glint patterns. As such, like your overall accuracy can come down. And also like eyelashes, embellishments, all these can affect the overall appearance models too. Then, yeah, when we are going to appearance models, we need good quality label data, like across users, diversities, and yeah, different kind of like eye disorders and all these things. One of the important problem is actually called as the slippage. So you see a user wearing a device here, and he does an eye calibration. But when the user actually starts moving around, the device is prone to slippage. So in which case, the moment it slips, your eye and your device center is not in actual sync, whereas the eye calibration you had done earlier kind of like fails overall. As such, like it might require repeated recalibration, and there are also methods recent like which explore online calibration given display-based devices. And finally, the important part is the privacy protection. Your eye is a lot of biometric and eye identity overall. So how can you anonymize your iris region so that like there's no hacking of your information overall, but still you're maintaining the overall gaze information here. Yeah, I'll end my talk here. So I call upon Satish, who leads the object perception, to talk on face tracking.
Thank you. Hello. Thank you for having me here. My name is Satish. I'll be talking on face tracking for XR today. Okay. So what is face tracking for XR? The face expressions behind this head-mounted device, we need to track it, capture them, and then animate an avatar. Now, this avatar that we are talking about can be a real avatar or a photorealistic character avatar. Now, depending on what we are going to use, the whole technology changes. We are going to see several technological components that enables these kind of solutions on these XR devices. Okay, so over the time, the technological components have evolved, starting from facial action coding system. Then something was built on top of that, which is blend shape animations, and then we have evolved to 3D morphable models. And now we are working on photorealistic rendering and using Gaussian splatting. Now, the thing is, in either of those systems or solutions that I just talked about, you need one or more of these components to build those systems or solutions. Let's see how. But before that, let's just see what these components are, and then let me walk you over how to build a system using one or more of these components. Starting with facial action coding system. So what is the motive? The goal is to encode the facial expressions on a face. Now, what is the intuitive way to do it? Is to group the facial muscles to specifically capture movements on your face. Like, for example, your left eyebrow movement. Group all the muscles that are responsible for left eyebrow movements and call it the fundamental unit. Here we call it action unit. So there are around close to 63 meaningful expressive action units that confine to the face. Now you can mix those action units in a certain way to actually build expressions, complex expressions, right? And then what we have is blend shapes. Blend shapes is actually built on top of action units. Now, blend shapes are nothing but 3D face shapes, which is, as the name suggests, right? It is 3D shapes which actually blend from neutral face to all the expressions of our desired choice. Now, each blend shape is nothing but it's a 3D shape where we are going to introduce some kind of distortion. That distortion can be a smile, it can be a frown, it can be a mouth open, and so on and so forth. Now, what we can actually do is we need to build weights around these expressions so that we combine them in a linear fashion to build expression of our choice. Commercially, there are certain blend shapes that are available in open source, like ARKit blend shapes, which are around 52 in number. Then we have OpenXR blend shapes, which are 63, MetaQuest blend shapes, which are also 63. Now we can use these blend shapes to build our own models. When it comes to academics, there is something called Face Warehouse. It comprises of 47 blend shapes. We can use them to build some POCs and stuff like that. Now, there are certain ways to make these blend shapes. Earlier, when there were no 3D scanners, we used to build these blend shapes right from scratch. We used to have these, build these dense correspondences from node to node, from neutral to all the expressions that we want, and then try to model them. But however, when 3D scanners have come into existence, all we try to do is have these 3D scanners, get the meshes, and then have the dense correspondences. There you have it. Then next is 3D morphable models. Now that we have talked about the expressions, right, transferring the expressions or capturing the expressions on the face, what we want now is to capture more than expressions. You want to capture the identity, you want to capture the texture, you want to capture expressions, you want to capture the pose, illumination, everything. Now 3D morphable models is the answer to it. So even in 3D morphable models, there are so many standards that have evolved. We have started with complete face and head model, then we have moved on to face warehouse. This is something that only talks about the identity. It captures the shape, just like what blend shapes did. Then face warehouse went a step ahead, and it has derived expressive low-dimensional linear space where you can actually use them to build any expression of your choice. And then BFM 2019 is different from BFM 2008, where BFM 2019 has evolved in such a way that it can actually express the identity, then you have the shape, the expression, and it can also capture the texture. And then Flame went a step ahead and added pose information. And there are certain other models that are built on top of Flame, which are IMOCA and DECA models, which have enabled, inherently they are using Flame as a 3D morphable model, but they are going to lift off from 2D to 3D. I'm sure everybody is aware of 3D Gaussian splatting, but this is one of the critical components. But let me just refresh your memories. Um, so, so what you see in the red here is a noisy, sparse point cloud. This acts as a geometric prior to this fascinating algorithm called 3D Gaussian splatting. And all it does is it tries to learn the scene so that it can render for novel views. Right? So what happens here is at every 3D point that you have here, you're going to place the Gaussians, and then you're going to learn the parameters. What are the parameters? You have the position, you have the color information, the opacity, and you also have the spherical harmonics, which is nothing but the color. Then what you try to do is you actually project it and then sort it in depth-wise order. Then you rasterize it, render it into 2D image, take the loss. There are two losses here. There is perceptive loss, and then there is structural similarity loss. And then you backpropagate it. Then every 100 or 500 iterations, you're going to check if the Gaussians that you have is dense enough or not. If it is dense, then you're going to remove some Gaussians based on some regularization. If it is sparse, then you're going to add or clone more Gaussians to make it dense enough, and then try to render the image. At the end of the process, you get 3D volume, which is what you're going to use to generate novel views. Now, these are the key components. How do we build a system out of it? Let's take an example, right? So you see here, this is the driver, and this is the source. Now, driver is driving the source. See how the expressions are being transferred here so seamlessly, right? Now, what is happening here? Let's see. Okay, this is the source, and this is the driver. And what we are trying to extract is there is a feature extractor which extracts all the features related to the appearance, right? And what is the goal of the driver is to induce expressions into the source. Now here, as an example, I've shown the source and driver are same, but it can actually be cross-subject. So which means whatever it is extracting from the driver is going to be independent of the facial appearance features, right? So what we try to do, we try to extract the implicit key points, which has correspondence to the key points in the driver. Then you have this transformation, which is nothing but the warping module, which tries to calculate the displacements of each key point from the source, trying to model the expression, and you warp the feature space so that what you get out of it is a warped appearance feature space, which has the appearance as well as the expression. Now, what sits here is a GAN model, which is a generative model, which generates the source image with an expression, right? So now, why are we talking about these is because we are slowly progressing into face tracking in XR. We'll see one more method. Here we're going to talk about Gaussian splatting too. So this is mix and match of all the components that we have seen earlier. There's Gaussian splatting, which builds a 3D volume of the source image here, sitting here. And here is a cross identity, which is a driver image. Now there is a combination here. This is a DECA model, 3D DECA model that is sitting here. What it tries to do is it tries to extract two things. One is the pose of the head, and the other is the expression, right? So this direction is the expression, and this direction is the pose. Now you have a template model here. Now what we try to do is you extract the appearance features of the face, and then combine it with the expression features from the driver, and try to induce those expressions onto the mesh. And likewise, you induce the pose onto the mesh. That is the top pipeline, which extracts the pose and expressive features from the driver. From the source, you are going to take the 3D volume representation in terms of Gaussian parameters. And what you try to do is you try to blend both of these things. And what you get is a 32-channel feature map. Now, that contains two things, right? It has the expression, it has the identity of what? Of the source. Now, what sits here is, again, a spade generator. It's a GAN model, once again. Now, generative model, what it tries to do is it tries to render the image, right? What does it try to render the image out of? Out of the Gaussian parameters, as well as the 3D morphable model parameters, right? So it's a mix and match of both the components that we have seen earlier. Now, it is so simple here, right? So you have a frontal face of a source, you have a frontal face of the driver, you're going to transfer the driver's expressions onto the source, right? But when it comes to XR, here are the challenges, right? So the driver doesn't actually have a face. It has certain images captured through sensors, right? So you have these eye tracking camera images and you have these face tracking camera images. What are you trying to do? You're trying to model all the expressions and the pose and everything from these images and try to induce into a source image, right? So that is the challenge. Now, if you look at it, these are the results that we have. So here is the stylized character avatar image that we are talking about, right? So you can pick any avatar of your choice, and the driver can actually induce the expressions onto the avatar. And likewise, we also have something called a photoreal, right? Photorealistic avatar. Now, there are two stages that are involved. One is the face registration stage, where it is going to build your 3D avatar, and then in the inference stage, it is going to induce all the expressions onto the avatar and animate it. So that's all I have. Thank you. Thank you so much.
We thank Dr. Pawan, Dr. Anup, and Mr. Satish for such an insightful and forward-looking session. Their perspectives on XR interactions and immersive vision technologies have provided a deeper understanding of foundations that enable seamless and transformative XR experiences.